You might remember this guy, Malcolm Gutenburg, a thermal engineer, and if you don't, he's the one who cut the RTX 4090 cooler in half with a water jet for us previously.
Stand by.
Malcolm is a thermal engineer at NVIDIA, and he's joining us again for another of our educational engineering discussion video series, and this time, he brought lasers.
So this is a laser interferometer.
He also brought this highly specialized acoustic testing senior technician. Today's content focuses on learning about the crossroads of thermal engineering, fan design, and psychoacoustics, as the three all converge in this confluence of science when building a thermal solution. And just like all our other engineering discussions, we asked Malcolm not to dumb it down, and he definitely didn't.
Optimize it for the human ear and use something called critical band, but it can be thought of as analogous to an overall 1/3 octave band. Centrifugal fan. I was talking about the fan affinity laws previously.
Yeah.
So P and Q are probably the most overused variables in thermal engineering. But so basically what happens is this is your maximum coefficient of lift.
Although not everything requires such technical terms.
Which might sound good if you're into EDM, but as far as the graphics card goes, not what we want at all, right? So,
although maybe a marketing opportunity. And as always, my objective in hosting these discussions is the same as yours for watching them. I'm here to learn from experts. Earlier, you asked a question of, do you do any prominence ratio, something or other after that?
Don't know.
And I was like, I don't know what any of those words mean, so I don't think so. As a great follow-up to our previous case fan engineering deep dive with Jacob Dellinger from Noctua, let's get started with this fascinating insight to acoustics, thermals, and product engineering.
Acoustics, thermal, performance, all kind of really tied together. So here we are in the acoustics lab. We got a lot of cool stuff, Hemi-Anechoic Chamber, and we really care a lot about the acoustics of our product. Not just the overall SPL, as we'll get into, the overall listening experience, how annoying something is to listen about or to listen to. So the psychoacoustic aspects as well.
Yeah, so the video today is going to be very focused on the engineering side of things, which will make it a lot of fun. So we've been talking for hours now with the whole team, and the various topics that have come up in psychoacoustics, measurement methodologies, things like Coil Whine, all this type of stuff. So we'll pick a few of those and get into them today. This caught my eye, and I did want to ask, what is it?
So this is a laser interferometer, and basically what it does is, you can see here it's shooting at a PCB. And we'll have this card running a certain stress test, any workload, and we'll have a mesh of different points there. So basically we'll have a set of different points along the board that we think may be causing any component noise, coil whine. And this machine here will shoot a laser at the board and then measure how much it reflects back.
Okay.
And then through that you can tell what vibration is going on. And typically the total amount of displacement here we're talking about is in the picometer scale, right?
Okay.
It's incredibly small. So it's a super accurate machine. Usually we have just a water block. We can expose the rest of the PCB. Yeah, it looks at how much is reflected back, and it can calculate what degree of deflection there is based on that. So it's a pretty fascinating piece of equipment. Takes usually it can take a while to run the full suite of the test, but the results are very interesting. On this case in particular, you can see that the inductors are usually causing the noise, but the noise might, and the peak vibration might not be corresponding to exactly where the inductor is.
Okay.
Because the whole PCB is kind of flexing. So depending on where that is, you can see sometimes it's the capacitors moving. So it's a pretty fascinating.
And this is where we get to earlier, your colleague Noah noting that coil whine can be a misnomer, I guess, because it might not be literally the coil.
Exactly, yeah. Sometimes it's the whole PCB flexing and moving that causes the noise.
Right. I don't know if we might come back out here later, but this is all hooked up as measurement equipment for what we're going to walk into, which is the chamber.
Exactly. We got a few mics going in the chamber right now, a mix of half-inch and full-inch mics. We'll get into the difference and why we might use one or the other. But you can see here, this is split up into 1/3 octave bands, We'll get a better idea of why that is later, how it impacts the overall user experience, and what it means to how the ear kind of perceives noise. Exactly. Yeah.
Okay, let's check out the chamber. So we're gonna. How's it going, guys? Hey, good to see you.
Good to see you.
Do you normally have this many people?
I have never seen more than
chamber.
5 people in the acoustic lab at once. I think it's a big moment. As you can see, right when you walk in, it's an incredible difference.
Door has a large impact as well, but we've already lost a lot of that echo. So.
Exactly. I mean, especially with 15 people outside, the door might be a bigger impact today than other days.
There are a lot of similarities in certain aspects of this chamber to the one we just had built.
Exactly.
So the wedges are very familiar to me because this is same type of wedge we're using where it's a perforated metal.
Correct.
And you've got, I guess, is it a fiberglass installation?
Correct. Yeah.
One of the topics from viewers we've had is, but why, right? Like, okay, we get it. You can get a really low noise floor. Nobody lives in a Hemi-Anechoic chamber. Why do you use a chamber in testing?
Yeah, it's a good point. And most people won't be subject to this level of quiet in their daily life. But for true engineering evaluation of any product, you really need to have a very low baseline to differentiate between what's background noise and what we can improve on the product. If your background noise is too high, then you're not going to be able to pick out specific frequencies or specific traits that could impact some users more than others, right?
Right.
So this is really the ideal case.
Yeah, and if you're in a large campus with a lot of moving people and parts, then...
Yeah, you're not going to be able to tell everyone at the door to please be quiet today. We're doing some acoustic testing on the second floor.
Blade design.
Yes.
We talked about it primarily from a thermal perspective.
Exactly, yeah.
You kind of briefly mentioned, there's acoustic considerations too. I know you've got a plan here for what you want to talk about. I'll let you lead the discussion.
So this is basically an evolution from our first axial design here, which is 20 series, to 30 series to 40 series. And the first thing you kind of notice is lower total blade count. So we went from 13 to 9 to 7 here. And there's a very good reason for that. It really has to do with those frequencies again, right? As you lower the overall blade passing frequency, typically we attenuate those frequencies more in our ear. So you can't hear those frequencies as well. So you want to shift that frequency as far down as possible.
Okay.
So reducing the blade count is a great way to do that. And also, as you go to a larger diameter, I was talking about the fan affinity laws previously. Yeah. If you want to maintain isoacoustics, you then run at a lower overall speed. You still gain airflow, and you run at a lower speed, and you have lower blade count. So it just benefits on top of benefits.
So if it's known that, in theory, you might want a lower blade count for acoustic reasons, because there's a lot of considerations that if okay, perfect world, I want lower blade count, how do you end up with the higher blade count still? I mean, what considerations are there in that design process, that make you not just jump to okay, this is the best fan we can make in the world, we're done?
Well, through time, I think we've improved our overall understanding of how the overall fan structure works. One of the key breakthroughs that we had was, if we look at these fans here, typically most of the noise is created on the leading and trailing edges.
Okay.
So the actual middle part of the blade doesn't create much noise, right? Much aerodynamic noise. So if we remove blades, you would think there would probably be an impact on either pressure or flow rate. But in reality, pressure and flow rate don't have an exact correlation. There's some empirical correlations. So for static pressure, typically what you want, static pressure is proportional to the number of blades times the blade length, right?
Okay.
So this length here.
Right.
So you would think, okay, reducing blades.
So you're not talking about this.
No, just the width actually. I guess.
Okay.
Yeah.
Sure.
Length. So you would think that if you reduce the number of blades, then therefore you reduce performance. But the key is to extend that to fill in the extra missing blade, right?
Right.
So you actually don't lose much pressure or flow rate by going to a lower blade count.
So is it primarily the thickness or the length, I guess, of the blade that helps to make up for the reduction in total blade count? I mean, is there an angle of attack that comes into play in the design?
Yeah, angle of attack is really important. So one of the goals when you're designing a fan is, for acoustic reasons and overall thermal reasons, is you want the velocity to be, the velocity of the air to be about constant as you move across the fan, right? But the problem is the tip speed here is 3 times that of it at the hub, right?
Okay, yeah.
And as you get closer to the center of the hub, it's 0, right?
Yeah.
So it's very difficult to create a uniform velocity gradient without twisting the blade. So you can see here on 20 series, there's a bit of a twist, but we've really gone to
When you talk about twist, where
this.
Okay.
Don't try this with your fans at home. By
right,
the way.
don't take yours apart this way. Yeah.
You can see here how the blade starts off at a shallow angle and then ends at a much sharper angle.
Right.
So the blade angle changes as you go closer to the hub, and the reason for that is to maintain the constant velocity across the fan blade, and the blade angle. The real key to the blade angle is avoiding stall, like I was talking about before. So basically, very similar to an airplane wing, you have stall issues where you have flow separation behind the leading edge of the blade in this case. And stall is really bad for acoustics because there's a lot of turbulence. It's really noisy and terrible for flow rate as well. So you really want to avoid that stall range. So if you look at this fan here, it's fascinating. It kind of looks like we had no idea what we were doing with the hub, right? I mean, all this wasted space. You think, man, these guys at NVIDIA have nothing going on, But there's actually a reason for this. So obviously with the FDB, we can go to a much smaller hub size if we want.
Yeah.
And that might be a good idea initially, but if you extend the same blade angle to that new hub size.
So effectively, you're reducing the total external diameter of the hub.
Exactly.
Okay.
And you would think, as a blade passes through the air, you have more overall net volume.
Yeah, you have more hole to push the air through.
Exactly.
Right?
You'd think this is fantastic. But the issue is, if you look at this fan here, you're pushing against a certain back pressure, right? So there is a back pressure there, and you'll actually start to see recirculation through the center.
Okay.
So you'll see negative velocity where that hub used to be. So you think, okay, well, let's just increase the overall blade angle at that point so we can reduce that recirculation. But then you start to get into stall issues and aerodynamic flow separation between the blade and the air. So this is actually the optimized hub diameter.
Okay.
Which is really interesting.
Yeah.
I think that was fascinating.
Because I guess purely from a physical standpoint, you have the space to shrink it down, increase the blade length.
Yep.
Right. I have some other questions for the chamber, but specifically talking about where stall region appears, I think on that curve might be
really
helpful
fascinating.
for people. So
looking at any fan, really the first thing you need to look at is what's called a pressure versus flow rate curve. So P and Q are probably the most overused variables in thermal engineering, but in this case it means pressure and volumetric flow rate. And for a given axial fan, you'll typically see something like this. And this hump is very important, but to kind of understand what this means, is this point here, if we just take this point, this is if the fan is just operating in free air with no blockage behind it. So no static pressure, it's just a fan.
So is this, if we take the common sort of acoustic testing setup, is this when you have a fan suspended and a circle basically?
Yeah. So this is typically the point where you see the acoustic value for a case fan. This is where you see the volumetric flow rate.
You'll get the highest number.
Exactly,
so,
it looks amazing, right? But the issue is, this is not where you're going to be operating at. There's, in any actual thermal engineering case, there's always going to be some pressure that you need to push through. And the pressure part is very interesting. Here, I'll use red. If you were designing something like a wastewater treatment plant or something, and you just needed to push water or push air through water, then the pressure you would need would just be the hydrostatic pressure of the water. And as you get to a laminar system, you'll have more of a straight line. But since ours is a turbulent system, we have a quadratic line that this is our impedance curve, and this line right here, so we can call this Q1, and this pressure here is actually where we're going to be operating at. And this point is really important because if we look at the overall efficiency of the fan, we need to make sure that this point aligns with the overall efficiency because typically the overall efficiency aligns within plus minus 5% typically with the lowest noise level. And you're thinking that doesn't make any sense because you're increasing the overall volumetric flow rate. You would expect more aeroacoustic noise, more broadband noise,
So if you were to add a right axis or something and plot noise on that.
So good thing we have 3 markers here, I guess. So here, if we just do SPL, right, we would expect something like this. But in reality, it looks something like this.
Okay.
And the reason for that is this area here is all stall.
So you don't want to be in this region.
You really don't want to be in this region. So basically what happens is this is your maximum coefficient of lift, similar to how an aircraft works or so. And after this point, the coefficient of lift drops right off. And this basically, if it wasn't for the fact that it's spinning around, you would get no pressure, no flow. It would be terrible. But since we're still spinning it around, it just basically becomes a mixed flow fan at this part.
So if we could see the air and you're looking at a fan and its blades, does that look different than when the air, when you're, say, at the operating point?
Oh, for sure, yeah. So you'll definitely see flow separation on the backside, on the trailing edge of the blade. You'll see a lot more turbulence. Turbulence is pressure fluctuation. Pressure fluctuation is noise. So it's certainly not something that you really want to be there. So one of the beautiful things is, the issue is you could say, okay, well, let's just move the operating point to the right? You get more flow, no problem. But the issue is you also want fins, right, for thermal surface area. So you want to add fins, but you also want to decrease pressure. And
and let's expand on that a little bit just for background. So adding fins, I'll take that part. You take the pressure
part. Go for it, no problem.
But, adding fins, the obvious, I guess, being surface area.
Exactly.
You want more surface area to help deal with the heat. How about the pressure side of things?
So the pressure side, I mean, you want more flow, right? You want more flow, and you want more fins as well.
Yeah.
So it seems like a bit of a
conflict.
Yeah, exactly. So the beautiful thing is, even if you just plot our east fan and our west fan on 4090, flow through makes a huge difference. So basically, instead of being at this line, you could be operating somewhere here, and then you can add more fins, and you can gain fin surface area and still be operating at that perfect, like, lowest noise, highest maximum, mechanical efficiency.
Right.
It's like the best of both worlds. It's one of the big benefits of blow through.
Yeah. And so chamber side, I guess, if we go back in with the fans. Can I ask about this setup first? Butcher block top's pretty self-explanatory, but how about what's underneath it?
Yeah, so this is a really interesting thing that we've just been kind of working with more recently. So for a lot of our testing, we want to be able to test while the GPU is running. We don't necessarily, if we just want to test fans, then this setup is totally not needed, right? We can externally power those.
Right.
But a lot of the times we want to look at electrical noise, we want to look at how everything kind of comes together as a final product, test fan curves, all that stuff. So for that, you do need a system. And as good as passive systems get, we also want it to be as quiet as possible and support a lot of power,
So is the idea that you put the host system in here? Is that
exactly?
Okay.
Exactly.
And then what? You run a riser up through a hole or something?
Exactly. Yeah.
Okay.
That'll and the issue is
cool.
with longer PCIe, like you can have those extenders, right? But you sort of lose out on
a lot of stuff. But
some insertion loss there.
Is this something we can show what's going on
yes,
here?
yeah.
If you come around here, Vitaly. Wait, let me get a.
Oh, yeah,
let's
the
let him get a
reveal.
shot. Yeah.
So this is how we dampen some of the noise that's created inside of the box there. We have a serpentine.
So is there?
There's the case fan there.
Okay.
And then the airflow will come up through here.
So is this is, I guess, it's pushing in. Is it effectively getting its air from up here through this hole?
Yeah, so there's a bit
Seems
of
like
pressure
a
drop.
long, yeah, it's a long path.
Yeah, it's a bit of a long path. Hopefully we don't have to support too much power in there.
Right.
But
So idea being that you're trying to get some cooling in for whatever's under there, but also, I guess, minimize external noise. Is
exactly,
that, okay.
exactly, yeah. So we try and keep everything as quiet as possible, but.
Do you have an exhaust on the other side or something?
Yeah, yeah. This one might be.
Oh yeah, okay, I see.
There you go.
Similar style, just
Yeah, exactly,
just
and then
pushes
goes
out
through the bottom. We try and get the airflow, exhausting out
right
below. And then, of course, we have a lot of microphones here as well. The main reason why we have so many is a lot of our products are very directional when it comes to sound.
Mm-hmm.
So depending on where you measure, you can have different overall sound pressure level values, different tones, different annoying sounds, right?
Yeah.
So we try and measure in as many locations as possible to simulate however users might use them, whether it's in a chassis normally or this way,
right.
anything that could in theory be used. And we have an assortment here of 1/2 inch and 1 inch microphones.
Can you walk me through, so at a top level, broadly speaking, what types of considerations are there when choosing the microphone for the chamber? Because you wouldn't want to take this lav, and use it.
Yeah.
So low noise floor is kind of the obvious one to me for the mic.
Yep.
But what other considerations are there?
So fundamentally, when you look at the microphone, it's just the top capsule there, and there's a diaphragm. And the diaphragm has a charge, and then there's a backplate with a negative charge. And you can think of it as kind of a capacitor. So as the diaphragm flexes, it changes the capacitance, and then you read that as overall pressure, and then you can take the root sum squared and get an actual value of what total pressure you would be able to see. So the bigger the diaphragm, the easier it is to kind of flex, right? So if you go to a 1 inch microphone, typically you have lower overall background noise that you can measure, right? So you can measure down to well below 0 dB. And the issue with...
I want to come back to that in a second too, but
yeah.
I'll let you continue on.
Sure.
Yeah.
And the smaller microphones, the 1/2 inch microphones, typically they're better for overall frequency range. So the human hearing range, like I said before, goes from about 20 hertz to 20 kilohertz. So you want to be able to capture that full dynamic range.
So you mentioned below 0 dB, which I think this is probably worth talking about.
Sure.
So scale doesn't stop at 0 here.
Yeah.
Is this something you can walk us through?
Yeah. So the whole dB scale is very interesting. It's fascinating. It has nothing. I don't think it was ever made for acoustics. I think it was made for telecommunications. I think Alexander Graham Bell, or I'm not an expert
right.
on that.
Yeah.
But it's just all of what the decibel is just comparing reference pressure value to whatever pressure value you're measuring. So let's say you measure a pressure value, divide it by 2 × 10⁵ pascals is the number. And then you take the log of that and multiply by 20. So instead of us saying this card is 0.0003 pascals, it might be a little more, confusing for the end person. So the decibel scale makes it a lot easier. So basically, if you're below 0, that just means you're below the reference pressure.
And then talking on the chamber side, because that kind of reminds me of Microsoft, I think, has one of the famous chambers for, if I remember correctly, I think it's underground or something. It's it's at least at one point had the quietest room in the world award. But there are different types of chambers too.
Yep.
So there's fully anechoic, hemi-anechoic.
Yep.
You've got a hard surface.
Yeah.
I think springs underneath.
Correct. Yep. So The hard surface is more representative of a typical user case. Typically, there's always kind of something below. So instead of using a full anechoic chamber, we use a hemi-anechoic chamber as it's more representative. You'll see the same things in like the auto industry because there's always a road beneath, right? So it gives a overall better representation of kind of the typical user
use case for the product.
Exactly.
Yeah, I guess testing a car suspended in the air in a fully anechoic chamber.
Yeah. And the reason it's kind of large, right? I mean, the GPU here makes it look a little
overkill.
Overkill.
Yeah.
But there is a reason. In case we make a lot more products than just
like DGX or something.
Exactly. So if we want to test, let's say, the full sound power of a given rack, a server rack, then we can put it in here and hopefully have, that's why the ceiling is so high, have the space required in order to test that. Also, as you go to a larger chamber, typically you can measure lower overall frequencies just because of, at the peak of human hearing, like the wavelength is incredibly small, like 17 millimeters, I think.
Okay.
But at 20 hertz, it's 17 meters long, right? So typically if you want lower overall frequency, you have to go to a larger chamber.
Right. My understanding too is that the wedge depth also affects the frequency cutoff.
Exactly.
How about do you spend personally, when you're doing engineering work, do you spend a lot of time on the fan curve and VBio, like figuring out the fan response?
Oh, for sure. Yeah, it's a very important part. Looking at how different parts of the fan curve, because obviously that PQ curve I showed is just for 1 RPM, and then you can use the affinity laws to kind of scale it based on RPM, right? So
does it hurt you when someone manually adjusts their fan RPM?
You can do whatever you want, but personally, I think this is the best one you can have. I'll stay out of that one. I think because we separate these two frequencies of the blade pass at least, right, by 25 hertz in order to try and give the best listening experience. So maybe you can think, oh, well, why do they even separate them? Let me just put them at the same level. But you might get a worse listening experience overall. Yeah.
Depending on where they land on it,
So to really get into some of the reasons we do the design changes that we do, you really can't just look at overall sound pressure level. So I know typically a lot of case fans and product reviews, you see just one level, SPL, this is what it is, and then the story kind of stops there. But you can have two different products, one with slightly higher overall SPL and one with slightly lower overall SPL. But depending on which frequencies are causing that or are prevalent in that tone or in that sample, you could pick the lower SPL version as sounding worse. One of the main things that we see when we look at the acoustics of our card is what's called the blade passing frequency. So every time you spin this fan, you have blades passing a certain spot, and those create pressure fluctuations in the air, and pressure fluctuations are what we hear. So both of these fans are 7-bladed, so they both, if operated at the same RPM, will have the same overall blade passing frequency. And if you look at a chart of the frequency versus SPL, you'll see that you'll see these tones very obviously in the overall frequency spectrum. So what we want to do is eliminate how annoying those sounds are, right? Because if you start to have tones stacked on top of each other, you really have a very unpleasant user experience. To really get into that, we need to think about how the human ear hears different tones. So we like to break up the frequency spectrum that we can hear from 20 hertz to 20 kilohertz into bands that we call critical bands. And I think most people might be familiar with the octave term.
Yeah,
so
sure.
An octave is a doubling of frequency. So if you go up an octave, you double the frequency. So if you break that up further into 1/3 octave bands, like I was showing on the screen out there, you get to a place that's more representative of how humans hear. So if a tone is in the same octave, 1/3 octave band as another, you typically can't really hear the difference between the two tones. So what we do is we further optimize it for the human ear and use something called critical band. But it can be thought of as analogous to an overall 1/3 octave band. And what we want to do is we want to make sure those two tones for a given fan don't overlap on each other, but we also don't want them in the same or too close to each other, because if the tones are in the same critical band but separated by only, let's say, 4 hertz or less than 25 hertz, we start to hear what's called modulation, which is this woo 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 woo, which might sound good if you're into EDM, but as far as the graphics card goes, not what we want at all, right? So,
although maybe a marketing opportunity.
Yeah, that's true. So we like to separate them by about 25 hertz. Past 25 to about 125 is what we call roughness.
Okay.
And roughness is much more desirable than pure modulation.
Okay.
Much less noticeable and better overall listening experience.
And so this kind of bridges into the topic of talking about psychoacoustics, where when I was first starting to, we only really got into past a dBA SPL meter in the past couple months, right?
Yep.
So total novice to this on my side. But we started speaking with Mike Chin from Silent PC Review, some other people, Eris from Hardware Busters, and one of the common themes I've gotten from people more experienced is I'll ask a question and approach it from sort of the scientific standpoint, and the answer I get back is like, well, this is kind of psychoacoustics, it's a special area.
Yeah, yeah.
Because you're talking about, it's not just the levels, it's the perception of the levels.
Exactly, exactly. It's very, very human, and it's looking at how we listen to different sounds, what sounds are typically louder and more annoying, and it's really how the inner ear is structured. There's two parts of the ear in general that really determine what sounds are annoying, what we hear louder. And if you look at the overall loudness spectrum, you can see that around 2 to 5 kilohertz are what we perceive as the loudest sounds, right?
Okay.
So those sounds, if we had ISO SPL, in those frequencies we would hear it the loudest. And that's because of how our inner ear or our ear canal amplifies those different frequencies. And then the frequency range that we hear is based on how the cochlea, which is part of the inner ear, perceives different frequencies. So it's this logarithmic spiral shape, which is very interesting. And you can pinpoint exactly what parts of that have different resonant frequencies.
Okay.
So as you get closer
cool.
to the center, you get to the lower frequencies. So you have 20 hertz to 20 kilohertz on average, right?
Yeah.
And if you were to just roll it out, I'm not a biologist, but let's say in theory you could roll it out. You have more linear space for the lower frequencies, which means, like I was saying earlier with the 1/3 octave band, the critical bands, you can typically differentiate between lower frequencies better. But in terms of overall hearing, based on how the ear canal amplifies different sounds, you can't hear those as loud. So it kind of all plays into that.
Right.
Yeah. But yeah, psychoacoustics, like you're saying, very subjective. There are some numbers that they put to it, right? What prominence ratio can be. Maybe we'll get into what that means actually. But
earlier, you asked a question of, do you do any prominence ratio something or other after that?
Tone to noise,
and I was like, I don't know what any of those words mean, so I don't think so.
So those, I would say those 3 items are some of the most important in terms of overall gathering how annoying a given sound is. So prominence ratio looks at the critical band. So you take that critical band and you take the average of that and then compare it to the average of the critical bands next to it.
Okay.
And then if it's above a certain level, it's very noticeable to the ear. And tone to noise does a very similar thing. I mean, tone to noise is very well named, I think.
Yeah,
it just
that
looks
makes
at the
sense.
tone, and then it looks at the critical band, so it looks at the noise. Both have their individual applications. If you have multiple tones in the same critical band, prominence ratio can be better at determining if that's going to be annoying or not.
Anything else in here that you want to cover, or externally?
No, I mean, the only other really, I think, fascinating thing when it comes to acoustics that's kind of really on the rise right now, because, when you look at a fan, I don't know when the first fan was invented, but probably like ancient Egypt,
probably a long time ago.
It's been a very well-developed industry, and you may think, okay, there's not a lot to improve nowadays. And if you just look at the fan on its own, free air, then it's true, there isn't too much, it's a very optimized fan. But as you start looking at it in terms of overall product, and you look at how each blade interacts with the fins, the heatsink fins, right? You can get some really interesting data. And we use Acoustics for this. So basically, you take this card and then you simulate a box around it, right?
Okay.
But the issue is at 20 kilohertz, your frequency or your wavelength is like 17 millimeters, right? And you want to have somewhere in the range of 100 points along that wavelength. So let's say you had this box that you wanted to simulate, and now you have to break it up into little cubes that are no longer than, I guess that would be 0.17 millimeters long, right? So it's incredibly computationally expensive. But the beautiful thing is, light propagation and acoustic propagation are very similar.
Okay.
And they're different, but they're relatively similar. So a lot of methods have been produced that use some of the ray tracing methods.
Oh,
so
interesting.
It's very similar to ray tracing. So that's why thermal radiation and acoustic, like aeroacoustic simulation, have like skyrocketed now because of how
in terms of computational time,
exactly.
like reduced?
Yeah, reduced.
Yeah.
So the abilities are amazing now when you look at how GPU accelerated some of these are. So I think it'll be revolutionary going forward. I mean, we've already learned a lot. Like even, for example, when you look at the blade shape and how it interacts with the fins and everything, it's like fascinating.
Yeah, it kind of comes back to what we talked about last time, which was NVIDIA in a unique position to use its own GPU hardware to simulate its own next-gen GPU cooler design.
A lot of the data center things that we've been doing just feed right back into G4. It's fascinating to look at, and it's like revolutionary for acoustics.
And like you're saying, back to total product level, it's also why you can have I think Noctua is fairly well known for the engineering focus. You have a company like them invent what is right now to them the best fan they've ever made, but then as they tune it for different products, you might have to tweak the design, which is something we have an interview with them about.
Oh, cool.
Just because at a product level, once you put a fin stack behind it, like
everything changes.
Yeah,
everything changes, and how you optimize the fins change too, right? And it's just fascinating to look at kind of the similarities to ray tracing.
Yeah. So next NVIDIA product will have ray traced air.
Ray traced acoustics.
Yeah, ray traced acoustics. That'll be on the marketing box with the actual ray tracing performance. Malcolm, thank you again for the walkthrough.
Always a pleasure. Always a pleasure. I love talking about this. It's fascinating stuff. We really care about acoustics, the overall listening experience. So, and what better place to do it than here?
And check out our last video with Malcolm. I'll link it below if this interested you. Thank you all for watching. We'll see you all next time.